Today we are diving into one of the absolute highest stakes battles in modern medicine, the fight against devastating neurodegenerative diseases like Alzheimer's and ALS. Now, for decades, researchers have been developing these really incredible treatments, but they've been hitting a literal physical wall in the human body. Well, today we're going to explore a fascinating breakthrough from MIT that is completely changing the game. They're using a totally unexpected twist in optical physics to illuminate the brain's deepest defenses.
Okay, let's dive right into this. Imagine you've got this highly advanced, potentially life-saving medicine right in the palm of your hand. You know for a fact it works perfectly in a petri dish, but the second you try to deliver it to a human brain, it is completely blocked. So how do you sneak medicine past the brain's ultimate fortress? This isn't just some hypothetical scenario. It's literally the ultimate biological mystery that pharmaceutical scientists are facing every single day. Because if we can't actually see how drugs enter the brain, we really can't design them to work effectively.
So, to figure out the solution, we first have to really understand the obstacle. That brings us to Section 1, the brain's ultimate fortress. We're talking, of course, about the blood-brain barrier, or the BBB. It is just an absolute marvel of human biology. It wraps our brain's blood vessels in this tightly packed layer of cells to block out dangerous toxins. But for medical researchers, this vital protector is an incredibly frustrating hurdle. It is so good at its job that it aggressively blocks out the vast majority of necessary therapeutic medicines we try to send in. Now, if scientists are going to design drugs that can actually cross this barrier, they need to watch them do it. But existing imaging tech has severely held them back. The old gold standard of optical imaging, it is agonizingly slow and distorted. By using common optical settings, researchers can only capture one flat 2D section of the vasculature at a time. To get the full picture, they have to run multiple, slow, repetitive scans just to painstakingly stack an image together. And worse, these older beams suffer from what are called side lobes. Essentially, these are blurry halos of light that distort the image, making it basically impossible to see exactly where a drug molecule is going at the microscopic level. All right, so the biology side was stuck. But then a solution pops up from a totally different discipline. Let's move to Section 2, a surprising physics discovery. We're zooming right down to the micro level at an MIT lab to check out a truly unexpected breakthrough.
The story kicks off with lead author and graduate student Hong-Hao Cao. The research team had developed a precise fiber shaper to tune laser light going through a multi-mode optical fiber. Basically, that's a type of glass fiber that can handle a massive amount of power. Well, Cao decided to push this fiber to its absolute extreme, dialing up the energy almost to the point where the glass itself would burn. Now, based on everything we know about physics, doing this should result in utter chaos.
Yeah, the common belief in optical physics is that if you crank up the power like that, the inherent imperfections in the fiber will just cause the beam to become wildly disordered and scattered. That was the expectation. But the reality? It was a shocking, happy accident. Instead of scattering into a mess, the chaotic laser light did the exact opposite. It spontaneously self-organized. It collapsed into this pristine, highly focused, single needle-sharp beam. No one saw that coming. Assistant Professor Sixian Yu, the senior author of the paper, perfectly captures the adventurous spirit of this whole moment. She said, "We followed the evidence, embraced the uncertainty, and found a way to let the light organize itself into a novel solution for bioimaging." I love that. They didn't just ignore this weird anomaly, they completely defied the common beliefs of their field, leaned into the mystery, and realized they had stumbled onto something revolutionary. Which naturally leads us to Section 3, creating the pencil beam. How exactly do you take a wild, seemingly random physical accident and turn it into a repeatable scientific tool? Well, the researchers figured out what you might call a self-organization recipe. And it needs two highly precise, kind of counterintuitive steps. First off, absolute alignment. The laser must enter the multimode fiber at a perfect 0-degree angle, which is a way more rigorous requirement than scientists usually bother with for these durable fibers. Second, you have to be brave with the dial. You literally have to crank up the power until the light starts interacting with the glass of the fiber itself. Normally, researchers avoid this high power out of fear of destroying their expensive equipment, which frankly is exactly why no one had discovered this before. So, why do these two steps actually work? It all comes down to a fundamental physical interaction. Right at that critical, high-power threshold, a property called nonlinearity kicks in. This nonlinearity actually counters the intrinsic disorder of the glass fiber. It creates this perfect balance that wrestles the chaotic input beam and transforms it into a stable, tightly focused pencil beam. And the absolute best part?
It does all of this without needing any complicated custom light engineering components. The light basically just organizes itself. Okay, so we've got this incredible new laser beam. Let's zoom back out and connect this physics breakthrough directly back to our original biological problem in Section 4, revolutionizing medical imaging.
When the researchers finally pointed their new pencil beam at a model of the human blood-brain barrier, the results just completely eclipsed the old standard. Instead of those painfully slow 2D slices plagued by blurry halos, the pencil beam captured the entire 3D volume of the vasculature in a single scan. It completely solves a classic imaging headache, that annoying trade-off between image resolution and depth of focus. Usually, if you want a deep image, it gets blurry. If you want high resolution, you only get a tiny, shallow slice. But the pencil beam, it delivers both, high resolution and a large depth of focus simultaneously.
And because it can capture the whole 3D volume without stacking up endless 2D slices, the sheer speed of this new method is just staggering. The researchers were capturing cellular-level 3D images roughly 25 times faster than the previous gold standard method. Just let that sink in for a second. 25x. A 25 times increase in speed means researchers aren't stuck looking at static photographs anymore. They can actually dynamically track individual cells gobble up drug proteins in real time.
Because at the end of the day, this isn't just about cool lasers, right? It's about what this means for human health. Let's bring it all home in Section 5, the future of brain therapies. MIT professor Roger Kamm really highlighted a massive benefit of this new tool. He stated that this new method doesn't require the cells to have a fluorescent tag is a game changer. For the first time, we can now visualize the time-dependent entry of drugs into the brain. This is huge, guys. Previously, scientists had to chemically alter drugs by sticking fluorescent glowing tags on them just to see them, which totally messes with how the drug behaves. Or they had to rely on animal models, which unfortunately often fail to accurately predict what happens in a human brain. Now, they can use human-based tissue models and literally watch native, untagged drugs enter the cells naturally.
So the crucial takeaway is this. The macro impacts of this pencil beam are set to radically accelerate medical science. By giving us real-time visualization of drug entry, scientists can now pinpoint the exact rate at which specific cell types internalize a drug. Plus, this technique isn't just limited to the blood-brain barrier, it can track all sorts of diverse compounds across a huge variety of engineered tissue models. Ultimately, this rapid, tag-free tracking is going to dramatically speed up the screening process for life-saving treatments for devastating conditions like Alzheimer's and ALS.
By embracing a totally unexpected anomaly in laser physics, these scientists have handed medical researchers a massively powerful new flashlight to see exactly what is happening inside our body's most secure vault. It bridges the gap perfectly between raw physics and life-saving biology. Which leaves us with one incredibly exciting thought to ponder. If we can finally see, clearly and in real time, exactly how drugs navigate the brain's ultimate fortress, what currently incurable disease are we going to conquer next?